Hello, everyone. My name is Bethany Frew, and I'm a researcher at the National Renewable Energy Laboratory. I work on computer models that span different timescales, focusing on both the planning horizon as well as the operational timescale. The title of my talk is Renewable Energy, Alternatives No More, and that's actually borrowed from a paper that I helped on a couple of years ago that's published in IEEE that really makes the point that because of technology improvements, cost reductions, and improvements in our knowledge of how to operate the grid, that renewables are no longer alternative sources of energy, but that they now have really become mainstays in our power system. And before I go any further in the talk, I want to give a few acknowledgments, especially to those in the Strategic Energy Analysis Center, where I'm located at NREL. These include Paul Denholm, Ali Allen, Clayton Barrows, and Aaron Bloom, who have provided different slides and content that I've used throughout this presentation. So one of the common criticisms that's given about renewables is, what about reliability? Can renewables supply a reliable source of power to the grid? Because really the ultimate objective of any power system is to provide a reliable supply of electricity to the grid at the lowest reasonable cost to consumers, so that when you turn your light switch on, the lights actually come on. And I would argue that they can, and it's because of some of these improvements that I'll be talking about later in the talk. But this issue of reliability, I bring it up now because it's going to come up a couple of times throughout the talk, again, because this sort of is what underpins everything that we do. So first, a little bit about NREL. We're located in Golden, Colorado, in the middle of the country. There is a whole series of national laboratories that are spread across the country. What's different about NREL is that we actually, everything that we do at the laboratory involves renewables in one shape or form. And that the scope of the lab can span things from policy analysis to people who work in a laboratory on materials research to make PV panels have a higher efficiency. There's actually a separate wind test facility located a little bit away from our main campus that they actually have a set of wind turbines, and they do different tests on those. There's also people like me who sit in front of a computer, and we work on computer models to try to simulate the grid to be able to answer how can we most economically plan the power system looking out decades into the future, and how can we most efficiently operate a given fleet on a minute-to-minute time scale. So the rest of the talk, I'm going to move quickly, and I'm going to kind of give a high-level overview first of how the electric grid works, then about how we do grid integration analysis. Then I'll talk about the impact that renewables have on the grid at different penetration levels. And finally, getting back to that alternatives no more and how renewables can actually contribute to reliability, I'll talk about some of the ways that with proper controls, renewables can actually help to solve some of the problems that they can create. So first, a little bit about the resources that make up our grid. This figure is a stacked area plot showing the sources that provided electricity in the form of energy, so in this case, terawatt hours. And on the x-axis, it's across different years, so starting in 1990 and evolving through 2015. So what you see here first is that the top bar or top area that's gray, that's from coal. So you see that coal dominates the power grid, but that contribution has been declining, especially in recent years. And instead, it's being displaced primarily by natural gas, which is sort of the olive green color in the middle. But what I want to really point your eye to is on the bottom right-hand corner, you'll see a tiny little yellow sliver that's barely visible to the eye from solar, and then a light blue section below that from wind. So solar and wind make up a small contribution to the overall energy supply in the U.S. power system, but that contribution has been growing rapidly. And so what are some of the reasons for that growth? First, it's because of economics, that the cost of both wind and solar, as shown in these figures with the blue bars, has been declining. Particularly solar in recent years, and I imagine many of you being involved in PV research are aware of this. And then on the right-hand axis, as shown by the orange-colored line, you see that the deployed capacity, or the amount of wind and solar load that's been built into the system, has simultaneously been increasing. Another reason for the growth in renewables is because we just have a lot of them in the United States. We have a pretty massive resource of various types of renewables across the country. This map right here is showing photovoltaics. And so as many of you know, PV resources are dominated or the highest quality is in the southwest portion of the country, as indicated by the darker shading of the color. If we look at concentrating solar thermal, or CSP, it's a similar story. The best resource is in the southwest part of the country. Wind, however, the best resource is in the plains in the middle of the country for onshore wind, And then for offshore wind, there's a lot of resource both on the east and west coast, as well as some in the Gulf and in the Great Lakes areas. And finally, biomass is a bit more distributed throughout the entire country. And so a key point here is just that, again, this resource is massive. If we look at some of the numbers for each of these sources, we're looking at gigawatts. And as a point of reference, the 2016 U.S. power system had about a total capacity of 1,000 gigawatts. So we're looking at orders of magnitude more available resource with just wind and solar alone here. Another reason for the large growth of renewables is policy. One example are what are called Renewable Portfolio Standards, or RPSs, which are state-level policies that mandate a certain amount of energy to come from renewable sources. And the requirements and the timelines for those policies vary from state to state, but this is just one reason that renewables are being built. Not shown here also are things like the Production Tax Credit, or PTC, which is a policy that gave a subsidy to the amount of wind production, a certain amount per kilowatt hour, that's actually being phased out after about 2019. So that's another reason for large deployment of renewables. So next, what is the electric grid? You can think of a grid as a large spinning machine that's rotating at about 60 hertz. And this graphic here, the blue images are showing different generators that are connected to the grid, and they're all connected to this spinning machine in the middle, and they're all spinning at that same speed. In the United States, 60 hertz is that target, but there are other countries that have 50 hertz as the target. So the features of this grid are that supply must always meet demand. And the reason that there's a sort of, in parentheses there, is that 60 hertz is the target. There are certain standards that are set by reliability organizations that basically have a slight tolerance band around that. So you can deviate up or down, and that amount will depend on the supply and the balance of supply and demand in the system. So if frequency is slightly higher than 60, it means that the load has either gone down or supply has gone up some, and vice versa. So frequency is one of the metrics that we use when we talk about reliability and stability, because it reflects the ability of the grid to maintain balance. Secondly, there are large hourly and seasonal variations in electricity demand. So absent of any wind or solar, load itself or demand has variability. There are also operating reserves to help maintain system reliability. Basically, we have a certain amount of capacity that's either set aside or that's been sort of flagged to be able to come online or to spin up to help provide backup if it's needed in the event of an unexpected increase in load or decrease in supply. This is also a very large industry, about $400 billion per year, and that's been about the same number for the past few years. So the grid itself, from where the electrons are generated at the generator to where it actually comes to the light bulb to lighten up your room. If we look at the upper right-hand corner in this slide, so the power is generated at a generator. It then moves through transformers to increase the voltage to a higher level. And that's so that it can flow across transmission lines across long distances to get to load centers. The reason we increase the voltage is because that results in lower line losses. After it's transmitted, it goes through a series of substations to step down that voltage to get it to the distribution level, either to the residential customers on the bottom right-hand corner or to industrial or commercial or business customers on the bottom left. The transmission grid itself is shown in this map of the United States. The different colored lines represent different sizes or different kV of the voltage level of the lines across the country. And the point that I want to make here is that if you look at the eastern half of the United States, you'll see that the lines are much more densely, there's just a higher density of lines. And that's because most of the load in the United States is located in the eastern half of the country. You'll also notice that there's not very many transmission lines that are flowing east to west direction across the middle of the country. And the reason for that, if we go to the next slide, is because there are 3 different interconnections in the United States grid. The Eastern Interconnection, the Western Interconnection, and ERCOT, which is most of Texas. So at sort of a different spatial layout, there are what are called NERC, or the North American Electric Reliability Corporation planning or reliability areas. And so NERC is sort of the reliability organization for the United States, and also into Canada and part of Mexico. But in terms of reliability for capacity purposes, so making sure that there's enough capacity built, they don't actually set the standards, they just monitor them, but they have a whole other set of operational standards, and we'll get to this a little bit later in the talk, that look at reliability from that operational timescale. But the point is just that there are different regions for these sort of reliability assessment regions, and there's actually sub-regions even within these areas shown on this figure. And then if we zoom down even further, there are what are called balancing authorities that basically are making sure that supply and demand are always balanced. And some of these balancing authorities, or BAs, are actually competitive wholesale markets. And so they have a whole market aspect that's tied to that balancing of the grid. And then if we zoom down even further, we see utility service territories, or load serving entities. And this is basically being able to buy and purchase and sell electricity at the distribution level to ultimately serve the end consumer. So I've kind of done a quick overview of what resources make up our grid, of what the physical layout looks like, but how do we actually plan and operate the grid? How do we make decisions about how to enable that supply and balancing the supply with demand? So it turns out that there are about 15 orders of magnitude involved in all of the various decisions related to running a power grid. All the way from decades that are years into the future on the far right of this spectrum, down to the sub-second level on the far left of this spectrum. And I think that we can kind of break this down into three main categories. On that far right, looking at the years and decades, is what's called the planning horizon. And so there's different types of tools and models that are used within each of these buckets. So there are planning models that specifically look out many years into the future. If we go one bucket to the right, we have kind of the main operations bucket, which actually includes everything. Sorry, one bucket to the left, includes operations, which actually can kind of go all the way to the left, but I usually think of operations as sort of on the minute or the hour or even the day time scale. And if we go all the way to the left from there, sort of at the second level, these are what are called the dynamic timescales, or things that typically involve electronic controllers that are automated, that ensure stability of the grid. So the work that I do is primarily focused on the right two bins, the planning and sort of the rightmost section of the operations bin. So when we talk about operating the grid, so I'm going to focus a lot of the talk on that operations, sort of the minute-to-minute balancing. If we look at sort of a simple solution for how we can maintain this balance, I like to go through sort of the supply and demand curve. And this kind of is getting more at those parts of the country that have a competitive wholesale electric market, where they actually do have generator bids and they clear at certain prices. And so this image is representing that process. And so what we see on the x-axis is capacity. And so that's either the cumulative capacity of your generators or your demand. So it's trying to find the balance of those two. And on the y-axis, we see marginal costs in dollars per megawatt hour. And so what happens is generators will calculate their marginal or their variable cost, and they'll bid that into the system, to the market operator. And the operator will take those bids and will sort them from lowest to highest, which is what's shown by this dark blue curve. And then where that curve intersects with the expected demand for that given time step, which is shown by the vertical dashed blue line, that's where the balance of supply and demand is met. And so if you go at that intersection all the way over to the y-axis, we see the marginal cost at that point, which is about 140,000 megawatt hours. The price is about $160 per megawatt hour. And so all of the generators that are at or below that point on the curve, on that supply curve, will receive that same price. And so this is a simple way for how a market will operate and how we can balance supply with demand. But there are a lot of other factors to consider. And so we can start first with thinking of this as a simple dispatch stack. So this figure is showing 7 days for a full week of load. And you see each day has a peak that represents the load profile. And on the y-axis, we see what the load values are. And if we consider just a kind of conventional portfolio or fleet of generators, which are shown by the different colors, we can do a simple sort of drawing horizontal lines and stacking this area the area under this curve to be able to supply the requirements for load. But the problem is that there are a lot of other constraints that are imposed by these generators that make it so we can't necessarily do this simple stacked dispatch. So first, we might have outages by certain thermal stations. So maybe, in this case, nuclear might have an outage, or one of the other thermal units, coal or gas, might have an outage, and so we couldn't rely on that certain band. There could be hydro constraints, which is the bottom purple colored area here, that hydro has constraints for water availability due to recreational or agricultural needs, and so the flow of water can't always be what you would expect. Maybe it's been cut down, and so you don't have the output from hydro that you would expect. There are certain ramping limits and startup costs for dispatchable, like quick responding generators, such as the gas units that are shown in the blue and the kind of pink color by oil at the top. And so maybe they can't ramp fast enough to be able to match this profile that corresponds to the shape within this curve, or maybe because it costs too much money for them to shut down and start back up. I've shown by the CTs, the blue tip on this, where these arrows are pointing on the 6th day of this week, that maybe it's too costly for them to just come on for that tiny little amount of time and then turn back off. And so maybe instead it makes sense for another unit to come online. There could be variations in heat rate or minimum loading, or what are called the minimum running levels or minimum generation levels. So certain generators can't turn down past a certain level. And so because of that, they might not, so in this dark purple section, the newer gas, maybe that unit isn't able to turn down as low as is needed to be able to match that load profile. So kind of looking at the valleys in these 5th, 6th, and 7th days. So these constraints make it a lot more difficult to be able to fill in this requirement for meeting load in this given week. In addition, there's a lot of variability in demand. I think I mentioned this earlier. This figure is showing demand for 3 different times of year: a summer period, a winter period, and a spring period. We see in the summer that there is a single daily peak. In winter, there is a double daily peak, and then in spring, it's kind of somewhere in the middle. And this is actually from the ERCOT grid. And so again, there's a lot of variability just in the load itself. And then when we start adding renewables to the grid, there are additional considerations. I think we can lump these into 2 categories. First is uncertainty, and second is variability. Uncertainty deals with the fact that we can't perfectly forecast wind and solar. Forecasts are getting a lot better, but this is definitely an area of continued research. Variability will increase our need for the frequency regulation. So if you remember back to that 60 hertz frequency target, and that frequency reflects sort of the ability of the grid to maintain a balance between supply and demand. So if variability causes that frequency to deviate too much, then we need additional reserves, frequency reserves in this case, to be able to support that change. The variability can also cause increases in the hourly ramp rate, so the rate of change with that ramp, as well as the range or the magnitude of the ramp itself. And so these factors are all shown in the figure on the bottom, where we see megawatts, so the instantaneous power on the y-axis, and then on the x-axis is time, and we see load in the blue, and we see an output from a wind turbine in red on the bottom, and then net load, which is just the difference between the two. So it's load minus wind, and you can think of that net load as basically everything the rest of the system has to be able to provide. And so we see how the variability, in this case, can cause the ramp range to be very large. It can cause the ramp rate to increase, and there's also uncertainty from forecast errors as well. So adding renewables to the grid changes our paradigm. It changes the way that we need to think about the grid, that simple rules of thumb, such as that simple dispatch text, perhaps, it makes that even more complicated. And so we need to be able to use sophisticated tools to do a proper analysis to assess how we can integrate renewables into the grid, and even without renewables, how we can most appropriately include all of those constraints so that we can efficiently and correctly dispatch the grid. So how do we do that? I'm going to talk through how we do grid integration analysis here at NREL. So step 1 is to buy some very expensive software. I imagine some of you have used PV science machines, so you might work on materials perhaps in a lab, and you have expensive machines that help you do that analysis. Well, in the same sort of vein, we have grid integration science machines, which are basically large computing facilities or machines that we log into and run our very large computers very large modeling runs on that can be very computationally intensive. And we have special software that allows us to simulate and replicate the grid and be able to account for all of those generator constraints and be able to account for the variability and uncertainty and all of these factors that must be taken into account. And so some of these simulations can consider thousands of generators and transmission lines. So there's a lot of pieces involved. And Security constrained unit commitment is just with determining a day in advance which units are going to be turned on and which are going to be turned off in the following day's operations. And then the economic dispatch refers to sort of the real-time how you're actually operating those units that have been decided in the day ahead that they would be turned on. So step 2 is to get some wind and solar data. And up until about 5 to 10 years ago, a lot of good quality data didn't exist. And we want data that is very resolved spatially and temporally. We want to be able to capture that variation in resource across the geographic area. If you remember back to those maps I showed earlier, we want to be able to capture that variability, and then temporally, the finer granularity, the better we're able to capture the variability in the temporal scale. Third is to calculate the change in reserve requirements. So one of the biggest impacts that renewables has on the grid is it increases the requirement for reserves. So both for frequency, which I mentioned earlier, but also just being able to balance the load and follow the load at a minute or hourly time scale. So there's a lot of reserve impacts that renewables have. So we've developed some methods to be able to calculate what that impact on reserve requirements would be. And so we put those resulting requirements into our models as sort of here's what the system has to be able to provide for different types of reserve requirements. And again, this gets back to that variability and the uncertainty pieces. Step 4 is to modify or enhance other data inputs to our models. A lot of this refers to parameters on our conventional generators, so things like, for example, our heat rate curves, which are shown on the bottom left. We want to make sure that we're capturing that heat rate curve, which is just that just kind of connects the amount of fuel that a generator needs to its energy or electricity output. We also want to be able to calculate and capture the emissions profiles of each of these generators. And we have very large data sets of historic and actual plants in the United States that we can capture a realistic representation of these. And then we hit the go button and we wait. Sometimes it'll take a few minutes, sometimes it takes weeks, depending on the size of the model. But once we get the outputs, we then ask a series of questions and sort of start digging into the results to analyze what's going on. So first we'll say, did the grid work? Did we break anything? Were we able to provide enough energy to meet the load at all times, or did we violate any reserve requirements? What were the impacts of that variability and uncertainty? Did we impact cycling costs and emissions of our thermal generators? Because of that variability, some of the other conventional plants will have to cycle up and down a lot more, and so that can have cost and emissions impacts. And what about the renewable output itself? Were we able to use all of it, or did we have to curtail or throw some of it away? And so in the end, what we have is a stack area plot shown on the bottom here, that if you remember back to that simple dispatch stack I had earlier, we now have something that's far more detailed and complex and reflects those complexities of a real system. So it looks much different than what we saw before. And so some of the other outputs that we'll see are things like production costs. So one of the key parameters is the total production cost, of how much did it cost to operate that system. And so we'll look at the differences between different scenarios to see the impacts of adding more renewables or higher natural gas fuel prices, or whatever the sensitivity that we are analyzing. So what have we learned from all of these studies that we've done over the past 15 years at NREL? And I say we, I haven't been around that long, but sort of collectively as a body of researchers and those contributing to this field, what do we know? So up until about a 30 or 35% penetration level of primarily wind and solar, we learned that, for example, integration costs, and I put those in quotes because integration costs actually deserve an entire talk on their own, and there's a lot of caveats and subtleties involved with this that makes this a very complicated thing to calculate. They're actually pretty modest. And I should say integration costs are typically, the way it's done is you run a scenario where you don't have any wind or solar. And then you run a scenario where you've added some wind or solar. And you take the difference in production costs between the two, and you say that's the cost of integrating renewables. But again, there's a lot more involved there, and I don't have time to get into it. But the point is that the impact that renewables have on cost is pretty small. That we've also learned that we can accommodate the variability due to wind and solar by using sort of the inherent flexibility of the grid, as well as some other low-cost options like increased balancing area cooperation. So that's just trying to capture, sort of pool reserves or pool your other resources across multiple geographic areas. so that you get the benefit of sharing and the benefit of, as the next point shows, of diversity. So there's a spatial diversity benefit from just aggregating wind and solar resources together, so it smooths the aggregate profile. So there's a lot of benefit in sort of increasing the footprint over which you operate a given area. Next, we've learned that almost all the wind and solar can be used, so we don't have to curtail very much, again, up until about a 30 or 35% penetration level. We've also learned that wind and solar essentially displaces the fuel use and the associated emissions from conventional plants, so it's a direct trade-off and a direct benefit. And we've learned that the additional reserve requirements have a modest impact on the emission reduction rate, because again, I mentioned that reserve requirements are one of the key impacts that renewables have that will cause a certain amount of additional fuel usage, but that's pretty minimal in this case. And finally, we've learned that storage, while it can help, is not necessary, and that at the current cost for storage, it doesn't make sense economically. So before I get to the next question that maybe many of you are wondering, well, how high can we go? I first want to just point out that we've already gotten pretty high, at least if you look at the global scale, and even here within the U.S., but on the global scale, there are many, well, there's only a handful, I should say, of countries, if you include hydro and geothermal in your resource or renewable resource designation, that are above 90% renewable. Brazil is above 70%, and then there's a couple of countries, Denmark and Ireland, that are on the order of 30 to 40% from wind energy. And if we talk about instantaneous penetration, because those numbers that I just quoted are looking at the total annual energy generation, but if we talk about instantaneous generation, which just means how much in any given point in time did wind and solar provide to meeting the load at that point in time. We've seen just this year, I mean, it seems like every month there are new records coming out for renewables breaking the penetration limit. And so in ERCOT, we hit above 50%. In March of this year, SPP reached over 52%. Ireland actually has set limits at 55% so that they don't go any higher than that. And not shown here, but Germany has already gone above 70% as well. And I think even in here in Colorado and Excel, they've gotten over 60% from wind. So there's some pretty large numbers that we've already reached. But how high can we go? And I think this is a kind of a hot topic right now. And what we've learned from our NREL studies of various geographic areas across the United States, we've indicated that it's possible to go above 50%. But once you get past that 30 to 35% penetration, it's kind of a key threshold, we're going to need a lot more flexibility. And I'm going to talk a bit here in a couple of slides about what that means, what are sources of flexibility, what does that look like. But first, this image on the bottom is from the Renewable Electricity Futures Study back in 2012. It was done here at NREL, and that showed that we could have essentially a huge transformation of the U.S. power system, going in this case from 2010 to 2050, going from a fossil and nuclear-dominated system to one that's dominated by renewables. If we get out transmission, if we design the grid smartly. So this sort of transformation is possible, but we have to be smart about how we do it. And really, once you get above that 80% level in the studies that have been done both here, because this electricity futures went to 80 and 90% penetration levels, as well as studies that have been done elsewhere, you start to get a lot of curtailment, and there are economic consequences to that. And so that tends to be a key limit, but it's not a technical limit. It really boils down to economics at that point, at least with the given cost and given set of knowledge that we have now. It's possible new technologies could come online. So again, going to this next slide, it really boils down to curtailment. I think that's going to be a key limit. At high penetrations, we start seeing the impacts of the coincident nature of wind and solar. So as you start adding more wind and solar to the system, you basically get diminishing value or diminishing contributions of those resources to the system, especially solar, because it's so coincident with each other that as you add more and more solar, you keep dipping into your net load at the same time of the day. And actually, while I'm saying that, I want to go to the graphics here at the bottom, which are from a recent study done here at NREL, the Eastern Renewable Grid Integration Study, or ERGIS, which looked at, you can see in this first image on the left, the entire eastern interconnection, so that actually extends up into Canada as well. And they were able to get instantaneous levels above 60% from variable generation. And one of the outputs from that is this, what's called the Duct Curve, and that's been a popular curve that's been kind of floating around in the power system world over the past few years. And essentially what that's referring to is, and again, this is another one of those stacked area generation plots. Is just showing the contribution from each of the generating resources to meet the load. And so if you look at the contribution from wind and solar, which are the top two, sort of the yellow and the blue on the top, and then curtailment's also there in red. But if you look at that profile, the resulting shape, again, is our net load. And that net load kind of looks a little bit like a duck. And so this, again, has been a popular image that's been used. But what's important here is to note is that sort of at the neck or the back of the head of the duck here is when the sun is starting to set. And so the system has to ramp up pretty steeply at that point. And you also see sort of the belly of or the back of the duck, how it kind of dips down, and that's because of that solar kind of eating into your load profile, resulting in this net load shape in the middle of the day where the resource is very coincident with each other. Another concern or kind of cause for this curtailment is what's called the min-gen problem, or the minimum generation. And I mentioned this earlier in the talk, but that just refers to the fact that certain generators can only turn down to a certain point, and beyond that, they have to completely turn off. And there is a cost associated with turning off and then turning back on. And there are other constraints that dictate, how long you have to wait before you can turn back on. Or if you wait too long, then it costs even more to turn on because you have to come from a lower thermal point. It's a cold start. And so there's all these considerations. And so sometimes conventional generators will actually run at a loss. Like they'll be operating when they're getting paid less than what it costs them to run, because it would be more costly for them to turn off and incur that shutdown and startup cost than to continue operating at a loss. So this is actually a pretty big issue. We're doing a lot of work with this throughout the lab. And sometimes those thermal generators have to stay online for operating reserve reasons, for reliability, going back to that first point of the talk. And so the point is that that minimum generation and then these reliability or the operating reserve point here prevents some of these generators from being able to turn down any low duct curve. It exacerbates sort of this issue of curtailment because we can't turn down the remaining system, and therefore we'll have to curtail more of the resource from wind and solar. So I want to talk about flexibility here. I'm going to go through a few examples. I really like this image, which shows kind of different buckets or categories of what are called types of intervention, or basically they're just different flexibility mechanisms. The cost, relatively speaking, is shown on the y-axis. These are sometimes called grid integration mitigation measures, so mitigating the impact of renewables. And so again, I'm not going to cover all of these, but I want to point out a few of them and some examples from what we've learned, particularly here at NREL. So first is looking at the dispatch sort of time operating horizon and how quickly dispatch is happening, so how quickly you're continuing to update your system with telling generators how to operate, and then also expanding the balancing footprint, which again gets back to that increasing your geographic area over which you're operating to be able to have more resources and greater spatial diversity. So this is one of my favorite figures. It talks about making operations bigger and faster. So what we see here is total regulation on the y-axis. So regulation is a type of reserve requirement. On the x-axis are sort of these three different panes. We see the size of the geographic area associated with the operation. So we have large on the left, medium in the middle, and small on the right. And then within each of these panes, we see different colored bars. And I'm not going to explain each of those numbers exactly, but essentially the larger the bar, the slower the operation. The slower both the dispatch, so when it's telling units to operate, and the lead time for the forecast. The point is that as you move from that green on the right to the lighter color blue on the left, your system is operating faster. It's updating the signal for the generators more frequently. And then as you move from the rightmost pane, the small geographic area, to the large area on the left, you see how that total regulation requirement continues to decrease. So having your operations faster and having your operations over a larger geographic area reduces your reserve requirement. I'm going back to the ERGIS, the Eastern Renewable Grid Integration Study done at NREL last year, and again, they were able to get to instantaneous penetrations near 60%. And among the different flexibility options that they used to enable them to do this, greater regional coordination or geographic coordination was among them. And so these 4 panes here represent different scenarios, going from a low variable generation on the top down to about 30% on the bottom 2. And so I think the bottommost was the more integrated system for the transmission. But basically, even with very large drops in wind because of forecasting errors, um, and that simultaneously the sun was setting and then a peak load for this certain period. So these 3 days on the x-axis, November 23rd, 24th, and 25th, were sort of the most stressful period over the period that they studied in this analysis. And so the system was able to maintain a reliable operating balance of the system despite these pretty significant events happening at the same time. And again, geographic coordination was one of the pieces. Another NREL study last year was the California Low Carbon Grid Study, which showed that getting to 56% wind and solar penetration is possible with less than 1% curtailment, which is awesome, is possible if, among other things, regional coordination is improved. And so this figure on the bottom is showing the curtailment percent on the y-axis and showing 3 different scenarios on the x-axis for the enhanced flexibility case on the left, and then conventional flexibility on the right. And so you see how having these additional flexibility mechanisms significantly reduced curtailment, moving from the right conventional flexibility to the left enhanced flexibility panes. So now moving to the transmission bucket. So basically, what if we build new transmission, or we enhance the transmission capacity of existing corridors? We can, again, tap into that spatial diversity benefit that we've seen over and over again in the analyses that have been done here. Next is looking at the dispatch of actually using renewables, so variable generation, to be able to dispatch them. And so one example of this is to use CSP, or concentrating solar power, which has an explicit storage component to it, so that if you look at the load and then the net load, with the net load is sort of this very variable solid black line. Power is on the y-axis, time is on the x-axis, and you see CSP is this orange block that's able to dramatically change its output profile to better match this net load profile to, again, accommodate the variability from wind and solar. Not shown here, but another option, such as what's done by MISO, one of the operating areas in the United States, is to have an explicit dispatchable program for renewables. So they actually require all new wind to be dispatchable, which allows the operator to manually turn them down in the event of, if there's going to be curtailment, then they can just turn that generator down. And by doing that headroom that's provided allows the wind to be able to ramp up and provide reserves with that remaining energy contribution if it's needed. So there's some benefit on multiple areas by having this dispatchable control of wind and solar. In that case, though, it was just wind. So next is flexible generation. So this is using your conventional generators, so coal, gas, and other thermals, and making them more flexible. And so this was looked at in the Renewables Electricity Futures study done back in 2012. On the left, we see the baseline scenario. On the right, we see an 80% penetration scenario, looking at 3 different thermal generators with time on the x-axis, power on the y-axis. And you see how going to this 80% penetration level resulted in a much more variable profile. And I should mention that 80% wasn't all wind and solar. That included hydro and biomass in that as well. But you see that these planes, if they cycled up and down, they were able to help accommodate the variability. And then the cycling issue was also looked at in the Western Wind and Solar Integration Phase 2 study that essentially found that even though there were increases in total production costs for this cycling piece, so basically these thermal generators are ramping up and down at a higher frequency, so they're having to move their machines around a lot more, and that costs money. That there's wear and tear to the units, there's additional fuel costs associated with that. And so this study explicitly looked at, okay, how much really does all of that cost? And then compared that to the savings, the avoided fuel savings by having that wind and solar displace conventional generation for much of the energy portion. And so basically the cycling costs were far outweighed, as shown in this image, by the avoided fuel costs. So next is to look at the load. It's the demand side of the equation. So everything we were just talking about was looking more at how do we supply electricity. But what if we talk about the other side of this and say, well, maybe we can make load be more flexible and make it more responsive so that it can better accommodate the shape of the profile of wind and solar. So this is kind of getting to the smart grid concept where there's communication between the end consumers and the the generators and the system to be able to have the consumers modify their profiles. So that can mean shifting their load to a different time. It can mean clipping the peaks, and so that you could avoid having to build extra capacity to meet that peak. There are also things like energy conservation and energy efficiency where we can reduce the overall load altogether. This figure shown here was from a study looking at the Florida system with a 30% PV penetration with as well as battery demand response. And so it's a simple graphic showing curtailment on the y-axis. And then as we move from the blue line on the top to the bottom, we have increasing levels of demand response. So we can reduce our curtailment. Again, that's one of the key issues and key limits with getting to higher penetration levels. We can reduce that curtailment by having more demand response. On a related point, it gets to this concept of energy systems integration, where not only are we trying to control the load that's already there, but we can try to electrify sources that currently are not electrified and basically add new load to the system, especially when we can make that load have some flexibility to it. So for example, electrifying residential heating, maybe where there's gas or other fuel supplied heating. It's electrifying transportation, so having more electric vehicles, and particularly where the charging of the batteries of those vehicles can be flexible to match, again, our wind and our solar profiles. And there are other commercial and industrial processes that we could try to integrate into that electric need, either through electrifying or even things like district heating or other heating uses that can capture some of the heat from other processes. And last, but not least, is storage. So there's a lot of research being done here. This figure is showing how the amount of curtailment on the y-axis with a given penetration level of wind and solar on the x-axis can be reduced by having larger duration of storage. So moving from either no storage from 4 hours, 8 hours, 12 hours to 24 hours. But we may have to accept just the inevitable truth that there's going to be some curtailment, that we might not be able to avoid this completely. This is particularly problematic in the spring where load tends to be relatively low. Wind and solar outputs are high, and in areas where there's hydro is also very high. You get a lot of runoff, and so we get into this minimum generation problem where you just can't accommodate all of the renewables. And we might have to come up with some new technologies to deal with seasonal storage. So a lot of the storage that I was showing is kind of looking at the 24-hour or so horizon, which is also shown in this image. It's showing how much curtailment can we avoid by using storage on the y-axis, given a certain amount of capacity, duration of hours on the x-axis. And if we have a PV-only system, well, then you're never going to have more than 10 hours or so, because that's how long the sun is shining. But if you have anything with a mixture where wind is involved, you're never going to get to a full reduction in curtailment, going up to about 30 hours here. And so we're going to need storage that can go across multiple months and capture some of these, curtailment in the spring and trying to move it into taking that energy and pushing it into the summer or the fall. So that might be something that we need to do for really high penetration levels. So this is getting up, above the 80% level. So what's next? What do we need to do in addition to these sorts of balancing studies that we do with grid integration? There's a whole other category of work that's being done on stability analysis. I don't personally do this sort of work, but it's important to note this to you. So I want to kind of quickly go over this. First is looking at our old system on the upper left, and I'm realizing I'm running short on time, so I'm going to move quickly here. We see, again, these blue sort of conventional generators all spending at the same rate. With our new grid, we're going to need to have what are called smart PV and smart wind, where they have controls. So these are all electronic control issues to be able to sense frequency. These are what are called inverter-dominated generators. So wind and solar, they have inverters that basically control the output. And so if those controls are programmed correctly, they can provide a lot of support and services to the grid to help mitigate some of the stability concerns that have been raised because of their addition to the grid in the first place. So again, we want to do all of these improvements and ensure these stability capabilities because of reliability. And you remember back in 2003, there was a large blackout in August in sort of the Great Lakes and Northeast area. I was actually living there at the time. So we want to avoid these sorts of events. We do this both by ensuring that enough capacity is built, so making sure there's enough megawatts in the ground at a given point in time in the future. And we also have operational constraints that make sure that the system can essentially respond whenever there's some sort of deviation or imbalance or problem, that the grid is able to respond and maintain operation. If these controls, again, are programmed and set properly, wind and solar, if they have those controls, can provide just as good, if not better, response than conventional generators. I'm not going to go into the details, but this is just showing voltage and power response. Wind is in the black, gas is in the red, and it just shows that the wind is able to get that after a deviation, which is shown by these little sharp dips going down in both of these figures, that wind is able to recover and help the system get back to a stable point more quickly than the gas turbine, especially if you look at the power case, how there's this oscillating shape with the red profile from gas. That's bad. So wind is able to do a good job, and on frequency response, it's a similar story. We see frequency on the y-axis and time on the x-axis. This is looking at a base case with little renewables and then a high mix of solar and wind in the red. And we see that with the right controls, that high mix, the red line is able to have just as good of response as the blue line. So to wrap up really quick, we've shown that up until, again, about that 30 to 35% penetration level, that we can have wind and solar on our system without a significant cost penalty. There can be significant emission reductions, and we don't risk reliability. But after we hit 20 to 35 level, we need to have a lot more flexibility. We're looking at 50% and over now. We're going to need any source of flexibility that we can get. And we've seen, again, really large penetration levels above 50% in the real world. And the last point, I think a completely renewable grid is possible. It's not going to be easy. We've always found technical solutions to our grid integration study challenges here at NREL. It just boils down to cost in the end. And we have to be smart about how we design the grid. It means we need to have the proper controls for wind and solar. And I didn't get to this point in the talk, but it also means that we have to look at the institutional side as well. That market designs, operational rules, some of these other factors are just as important to make sure that we allow wind and solar to be able to provide those services that they can contribute to maintaining reliability. And so I'm going to leave this graphic showing up here in the back if I can figure out how to open up the question bar. But this is from our URGA study on the eastern half of the U.S. and then the WEC on the western half, sort of a time-lapse graphic showing how different generator sources provide electricity throughout the day. And you see right now the sun is setting as it's becoming dark and conventional generators are coming online. And then the sun will rise here on the upper right. You'll see it come down. And then the solar will start to fire back up. Yeah, so it's turning yellow there. And then the circle images on the left and the right are showing the transmission flows between different regions and how those change as the different resources are producing throughout the day. So I'm not sure if I can leave this up. I might have to, okay, I'm going to have to exit so I can see if there's any questions. Jonathan, I don't see anything. Oh, someone's typing.
So
okay, now I see.
You need to stop sharing your screen. That's that, and then it will. So.
Oh, great. Okay.
Okay, you should be able to see it now.
I might need to click on something. Oh, I see. Does this simulation consider harmonic distortions in the grid? Which simulation? So, I mean, that's all on the dynamic side. I personally don't do any of that research, so I'm not sure that I can answer
that. Hey, Bethany, I've got a question from here at UT.
Sure.
Hi, my name's Dan, Dan Hauk, and I had a question about time of use pricing. I don't know if you went into it at all, but do you think time of use pricing would kind of help make the cost of implementing solar more viable or less viable?
Yeah. So there's a lot of people looking at that, and Personally, I think real-time pricing might be more efficient, just because with the time of use, you're having to assign a preset time and preset rates for those time periods. And so as the grid continues to evolve, maybe we could tweak those definitions to capture a good um, the right sort of profile for the current system. But as things continue to evolve, there has to be some sort of ability to send the right signals, right? I mean, that's the point of the time. Any of these sorts of pricing mechanisms is to try to send the right signals for having demand respond in the way that the grid needs. And so if those signals aren't replicate or aren't referring or what's the word reflecting, I guess, what's going on in the real system, then they're not going to be as useful. So I think real time is probably where we ultimately want to get to, just because that would have a more efficient signal being sent to the end user to be able to best adjust their usage for what the grid needs. But time of use would be a step in the right direction, as long as again as long as there aren't any unintended consequences from that, right? That if we define certain time blocks and then we end up, because of other changes to the grid, that is not the right sort of signal that we want to send. We could have some unintended consequences, but and I should say I'm not an expert in that area, but that's from what I know, that would be, I think real time is where we want to ultimately get.
Okay, thank you.
Oh, someone else typed one. Oh, I didn't mean to say that short-term storage is not helpful. Storage is definitely helpful. My point was that at the current cost, so the current cost points, that the storage just isn't economic. That in the studies that are being done here, and Paul Denholm was probably our, really a world expert in storage, at least from the grid integration side. It just, the economics don't work out. As costs continue to come down, we'll get to a point that maybe it does make sense, but I mean, CSP certainly has a lot of value in being able to have that storage piece. That's what allows it to be quote unquote dispatchable. Yeah, so I didn't mean to say that they weren't helpful. They definitely are. It's just an economics question. Someone else is typing right now too. You're welcome. Maybe not. Oh. Yeah, that's a great question. Okay, so the question is about how far is the U.S. off from being able to hit an instantaneous level, like in the 70%. I mean, the SPP and ERCOT, I mean, that's where you see a lot of high penetration of wind, and those are hitting, above 50%. So if we look at the U.S. on a whole, I think we're pretty far off from that number, from anything, even above 50% as a whole, because there are certain parts of the country where there's very little renewable development. I don't even think I could speculate for when I think that would happen, but I think we're a ways away still. I see someone else is typing. Okay, so the question is about with coal being on the downslope, is it inevitable that the areas where there was coal will become more renewable? I would hope to see that, but I mean, gas is really what's been driving coal out more than anything. And I should also mention that load actually hasn't been growing at the rates that it was predicted to grow. And so in many parts of the country, actually as a whole, we have excess capacity on our system. So that's kind of another complicating factor in a lot of this, is that there's just not a lot of need for capacity right now. I think that'll change, especially as more coal keeps retiring. But I think a lot of areas are replacing coal with gas. But the cost of renewables keeps coming down, and it is more economic. It seems like every year. So I think we'll continue to see renewables on a whole continuing to be built more. A lot of the talk of what we need in the system is more about flexibility. I like to say that not all megawatts are created equal, and And to the point that, not every generator can provide the same sorts of services, but there are different characteristics that are just inherent to different types of resources and those generators. And so it might be such that we start looking at the types of services that we expect the grid to need in the future, and then we start building resources that can provide those services. Oh, yes. So Paul Denholm is the storage guy. He's done a lot of work with CSP as well, in particular. You're welcome. Okay, so the question is, if storage is the most important aspect for renewable becoming the primary provider, given the size of the United States? I think storage is really important. I also think that some of these institutional factors are really important. I guess it's sort of how accepting are we of high curtailment levels? How tolerant are we of that? How much are we willing to pay? What is our ultimate objective? Yeah, I think, I don't know if I would think it's the most important. It's definitely up there.
Okay. Well, it sounds like we've actually had some really good questions. So thanks for everyone who submitted those. If there aren't any others, I think we can let Bethany go. Thank you very much, Bethany, for a really great and interesting talk.
Great. Well, thanks for having me. I appreciate the opportunity to share this with you guys.
Absolutely, and please, if you get new data in the future and want to come and give another talk, an update, or anything like that, please feel free. We're always interested.
Will do. And I should also say, if any of you are interested in have any other questions, feel free to email me. My email was on the last slide, but I kind of closed that quickly, so I don't know if anyone saw it. I guess if Jonathan, you can just give it to them if anyone asks. Is that a good way to do that?
Yeah, absolutely.
Perfect.
Okay, well, thanks again, everyone, for attending, and thank you, Bethany, for your time. This is an ongoing series, so please join us again in the future if you're interested in talks about renewable energy. Thanks again, everyone.